introduce, okay, Evan Reed. Is he there? Oh, yeah.
Yeah, I'm here. Can you hear me?
Yes, we can hear you. Thank you so much for joining us. And I'm looking forward to your talk. Very early? No, no, we have 2 minutes before the hour. 9 o'clock, it's not so early. 9 o'clock in California. It's not so bad. Even has had time to have breakfast. Anyway, let me first introduce Professor Reed. He's currently at Stanford University, where he's in the Material Science and Engineering department. He received a BS in Applied Physics from Caltech in 1998 and a PhD in Physics from MIT in 2003. Then he moved to the Lawrence Livermore National Laboratory and finally moving to Stanford in 2010. And his talk sounds really interesting. He's going to talk about materials that have yet to be synthesized, yet should be synthesizable. And he's going to talk about more than 1,000 materials that are likely to exist, but yet do not currently exist, it seems. That sounds very exciting, and it's fantastic, because then you can theorize without having the problem of having experimentalists tell you you're wrong. So we look forward so much to your talk, and please, please begin. Thank you.
Well, great. Thank you very much. Thanks for the introduction. And let me see if I can go to full screen here. Okay, how does this look? Can you see the full screen?
Looks good. Thank you.
Okay, fantastic. So it's a real pleasure to be here virtually anyway. And I'm looking forward to the opportunity to meet some of you a little bit later. And this work is focused really on one of the grand challenges for computational material science and theory, which is really focused on this question of what is possible to exist that doesn't exist yet. So the context here is that there's, of course, been decades of work focused on thermodynamic equilibrium properties of materials, and that aspect is really relatively mature, becoming relatively mature. But there's still open questions about how to predict what's likely to exist. And part of the challenge is that the physics and chemistry associated with these predictions is really quite complicated. And it involves, for example, metastable states of materials, because many of the things that are made in the lab are actually in a metastable state, understanding what determines metastability and the different types of metastability that play a role. These are very challenging things to tackle from traditional physical and chemical perspectives. And so this area has been relatively slow to develop relative to the thermodynamic understanding of materials. And so my plan today is to talk about what's new. And so there are opportunities, I think, to tackle this in a slightly different way by relaxing a little bit of the physical understanding that we have of the process, getting a little bit away from the detailed physical modeling and replacing some of that with data, because we do have an increasing understanding of, for example, the things that can be made in the lab. There are a growing number of databases of crystal structures and other types of information that can be used for this purpose. So the idea here is to consider this kind of different scale at which you might be able to make these predictions. And so I'm going to do this in the context of low dimensional materials, which include the 2Ds and also some 1Ds and some other things, which I'll walk you through. In part because there's a lot of action in this space. I think there have been you've had at least one or two talks earlier in the session about these materials, these 2D materials. So first of all, in order to take an approach like this, one needs examples. You need data. And in our experience in this space, data is the most critical thing. Understanding the data, having all the metadata, data curation is really what determines success or failure of approaches like this. It's not the sort of machine learning model Even features are less important. Data is really the key thing. And so I'm going to spend some time talking about where we get our data. And specifically, I'm going to talk about a database that we put together some years ago to identify the spectrum of layered materials that have been synthesized already. So this is our database of known examples of layered materials that are likely to be exfoliable into 2Ds. And then I'm going to talk about how to combine this with some known physics and chemistry to actually try to predict what 2D materials are likely to be synthesizable but have yet to be synthesized. And how many of these are there? To what extent can we determine their properties? And then also, perhaps most importantly, under what circumstances should we believe these predictions? Because we're getting a little bit away from physics, we're augmenting it with some data, and there are real opportunities to be led astray. If the data is sort of not sampled in the right way, and so we worry a lot about this, and so we spend a lot of time trying to figure out how to benchmark models like this. How do we know when we should believe them? And so I'm going to walk you through several ways in which we've done this. One of which is comparing to humans, to expert humans and synthesis chemists, to see how this model does in comparison to them. And then if I have a minute left at the end, I want to talk about what this really enables. So there's a lot of work happening in this kind of space of machine learning and materials and different subdomains of material science. And a lot of it is really aimed at doing things faster that we could do before. But I think there are also some opportunities that are really being enabled by this that were not possible before, and that I think are quite exciting. So I want to just walk you through at the very end just a little bit of sort of what I think is the impact here. Looking, say, 10, 20, 30 years down the road, what is really going to be the legacy of this era of exploration of machine learning and material science? What are the things that are going to come out of it that really have impact down the road? So that's the layout for my talk. And so first of all, let me talk about this database. I want to spend about 15 minutes or so just talking about where this data comes from. So the goal here is to construct a database of layered materials that have been synthesized. So these are all materials that have been synthesized and characterized, reported in the literature at some point in the past 50 years or so, and then scraped out of literature, put into one of several publicly available crystal structure databases, including the ICSD database. And then we take these databases and we've developed an algorithm, which I'll talk about here, that goes through this to try to identify which ones have a layered nature to them. So these are all materials that have been synthesized, and this is essentially the algorithm. So the algorithm goes through the contents of the unit cell of the crystal and first identifies the bonds. So which clusters of atoms within the unit cell are bonded to each other. So it determines these clusters. This is just based on a simple bond length criterion. We don't want to have to do DFT, any kind of DFT calculations for this. So it has to be fast. And so we're just using a simple bond length criterion to determine this. And once we have the clusters of atoms that are bonded within the unit cell, we use a topological algorithm to determine the dimensionality of those clusters. So for example, if your unit cell in 2D here consists of, say, molecules, for example, which have a zero-dimensional structure, and you, say, make a supercell now, you make a 2x2 supercell of that unit cell, and you reevaluate the number of bonded units within that cell, you find that you get 4 bonded units if these are zero-dimensional objects. But if you do the same trick with a one-dimensional structure, let's say you have one-dimensional wires running through your unit cell, and you make this 2x2 supercell, and then reevaluate the bonded units, you find that now you only have 2 bonded units within the supercell. And that tells you have essentially one-dimensional wire-like components in your cell. And same thing with the 2Ds. So if you make a 2x2 supercell in this 2-dimensional example, you would get 1 bonded unit. And so this is essentially just a topological algorithm that can identify layered materials independent of any kind of deformations that they have. So if they have corrugation or they have a more complicated structure, they're not just flat, planar materials, this will still allow you to identify these. So when we did this, so actually we did this work, maybe it's been about 7 years or something like that since we did this. And we initially came up with about 1,200 2D materials. And since then, we just keep rerunning this algorithm about once a year on these databases as the databases grow, like the ICSD continues to grow. So we just keep running it. And I think we're up to about 2,000 now. So there's something like 2,000 known synthesized layered materials. But in this particular example, we're running with this 1,200 number because that's what we had when we did the work. So when you look at these, there's a real broad spectrum of morphologies of these materials that are really quite different from the usual suspects like graphene and the TMDs, the ones that have received the most attention. Most of these materials are really quite thick. The layers are thick. Like this cadmium compound here is maybe something like 9 or 10 atoms thick, and they have very complex low symmetry structures. There are also materials that have multiple polymorphs. So for example, this manganese compound has one polymorph, which is has flat layers. And then it has also a similar energy structure that has corrugation in the layers. And so there's some kind of symmetry breaking that can occur that will lead to this transition. And there are actually quite a few materials that have these kind of relatively low energy polymorphs. Furthermore, there are materials that have perforations. So graphene, one of the kind of unique things about it is it's relatively impermeable to just about everything. And but if, let's say we're interested in ion filtration or ion conduction, maybe small gas molecule trapping, those kinds of problems, something with some perforations might be of interest. And so there are actually quite a few materials like this vanadium compound that have layers with holes of various sizes that might be of interest for applications like this. So there's really quite a diversity of structures that are in this database that you find that are really quite different from the ones that have received the lion's share of attention. And so one of the challenges of having 1,200 materials is trying to make some kind of sense out of it. So how do we categorize these in some way that we can kind of understand without having to actually go through and look at all of them? So this is one of our attempts to categorize these in terms of chemical families. These are families that all have more than 5 materials in the database. So perhaps not surprisingly, the chemical family that has the most examples is the TMD family, like molybdenum disulfide and tungsten diselenide and so forth. And these, so once one example, like let's say we know that MOS2 has a layered phase, you can make some pretty good guesses that maybe W S2 would also have a layered phase, or might be more likely to have a layered phase. So you can certainly, given one or two examples, you can certainly extrapolate and make guesses via elemental substitutions on the sizes of these families. But one of the big surprises that came out of this is that most of these materials, more than half of the materials that we found, are actually one-off examples. So there's only one member in the chemical family, and there are no other, if you consider elemental substitutions, there are no other example, no other known examples. And so these are cases you would not find by simple elemental substitutions, chemical elemental substitutions. And that's more than half of the materials in the database. And so certainly, the sort of traditional approach to figuring out what is synthesizable, given some information about what is known to be synthesizable, is through these elemental substitution considerations. And that, in the case of 2Ds, that certainly gets you, pretty far, maybe half of the possible materials, but you're still missing about half, which I think is interesting. And so we would like, ideally, an algorithm that is capable of identifying those other half, the ones that are not simple elemental substitutions on known compounds. If you look at the band gaps of these, there's a huge spectrum. Pretty much any band gap you want, you can find a material in the database that has it. There are about 300 metals. So if you're interested in heat spreaders or conductors, and you don't like graphene, there's a lot of other candidates in the database. Optical properties as well. There's a whole bunch that have optical gaps, and even very large gaps, like typically we consider boron nitride for very large gap insulating applications, but there's probably a couple dozen other materials, mostly oxides, that have gaps also above 5 electron volts. And so there's really quite a bit of diversity even in electronic properties in this database. So in the process of doing this, we also identified crystals that consist of one-dimensional van der Waals components. And these are really, they receive far less attention than the 2D counterparts, although one could argue that they have likely have a lot of the same properties as the 2Ds that make them potentially useful. And one of the aspects of the layered materials that makes them interesting is that you can thin them down to very, very thin films and have their properties be relatively unchanged. And that's a useful property, for example, for something like electronic interconnects in electronic devices, where you want to be able to have, for example, a conductor that maintains its high level of conductivity in film thicknesses that can be scaled down to nanometer dimensions. There are lots of applications like that where you really don't want any of this interesting nano scale stuff. You want to maintain the bulk properties down to very thin films. And these 1D wires are probably also in that category. And so there are a few of these that are well known, like tellurium and selenium, that exist in 1D spiral chain sort of structures, like 1D atomic wires that are helical in nature. And there are a few others that have been studied, like these tantalum selenium wires. Some electronic properties have been studied in these. There's also some work in the 90s on a few of these chalcogenide materials in a superconducting context. But apart from that, there's really been relatively little focus on these materials. And so we also got interested in these, and we've been working on these. And you can categorize these into chemical families as well. And when you do that, you find that some of these wires are straight. They have, this is the This is the wire. We're kind of looking down the wire axis in the unit cell here. And others are helical and chiral. And this is something that we've been very interested in because we think it can lead to some very useful properties for electronic devices. And so I'm not going to talk about this today, but I think the sort of diversity of materials here in the 1D space is also potentially very enabling, and it's fertile ground. There's been very little work in this space. So if you like 2Ds, but you think the field is crowded and you're looking for something new, you might consider these 1Ds. Gaps also are, for the 1Ds all over the map, you can find, some kind of material for the particular gap that you're looking for. Many of these are metals, but there's still a broad spectrum of gaps. We also found, switching back to the layered materials, we found that some of these materials that have been synthesized are actually synthesized naturally through some combination of thermodynamics and kinetics. They wind up in phases that are layered, but have dissimilar layers. So in the case of MOS2, the unit cell looks something like this. There are two layers in the unit cell, but they're chemically identical. They're both MOS2 layers. In some of these other materials, like this yttrium compound here, there are layers, but the layers are chemically dissimilar. And so these are really like heterostructures. So there's been a lot of interest in trying to stack dissimilar layered materials manually, or grow a sequence of different layered materials on top of each other to create vertical heterostructures, which could be useful for electronic devices, optical devices. We can think of this as a sort of a junction. You can categorize it into a type of junction depending on the band alignment. There's been a lot of work on studies of excitons, bilayer excitons in materials like this, and so forth. And so, but the work that's been done has involved manual stacking of dissimilar layers. But what we found here is that there's actually something like 100 materials that, for whatever thermodynamic reasons, wind up forming crystals that have these dissimilar, that are essentially vertical heterostructures. And we've done some work on this too, to study the electronic properties and the band alignments in these. And we found that some of these could be very useful for very high surface area optical detectors, and potentially also emitters, depending on how the bands are aligned. And so I think there's opportunities here as well to extend this notion of vertical heterostructures to very large surface areas, essentially bulk crystals. In addition to just layered heterostructures, we found that there can be mixed dimensionality heterostructures as well. So in this particular example here, this mercury compound, this is a 2D heterostructure, and you can see that from the plan view here on the side. There are mercury atoms that exist in one of these two layers. This layer does not have the mercury atoms. This one does. They're the silver atoms. And this is actually something that is mined. This is called Livingstonite, and it comes from a very specific mine in Mexico. It's a mineral, and you can find this stuff on eBay. One of my students found a sample of this stuff. Some rock collector had it, and we got it, and you can exfoliate it and you can study it. And so some of these are relatively easy to find. In addition to the 2Ds, you can have mixed dimensional. So there's 2D plus 1D structures like this guy. This is one that has a 2D layer, and it's got 1D wires that are running through the unit cell. They're running in a direction perpendicular to the screen. And then there's even 1D heterostructures as well. So these are all 1D wires, but they are of a dissimilar chemical composition. And so there's quite a diversity of these heterostructures as well. So to some extent, you can categorize other properties of this spectrum of over 1,000 2D materials. You know, and most things require some kind of electronic structure type calculation, so that makes it a little bit more challenging. But there's still some things you can say just based on, for example, the symmetry of these materials. When you exfoliate a single layer or a bilayer of these materials, the symmetry of them can be different from the bulk. And so it's possible in some cases for some properties that are sensitive to the symmetry to emerge as you exfoliate a single layer. And these properties can be properties that you would not find in the bulk. And one of those happens to be this piezoelectric effect. This is something that we did almost 10 years ago for the TMDs, predicting that the TMDs would have actually piezoelectric effects that the bulk TMDs do not. So if you have a 2D layer and you peel it off the bulk, that's gonna have a piezo effect because it has no inversion center of symmetry, whereas the bulk material does not have this effect. And so this is something that we predicted, and there were a series of experiments following up on this, observing these effects in a spectrum of materials. And what I'm showing here on the slide were just some of the first experiments, and there have been a lot since then. So if you've done one of these, I apologize that it's not here on the slide. I'm just showing some of the initial ones. And they've been observed in a variety of different materials as well. So not just the TMDs, but some of the more exotic ones like this C3 and 4 structure here that has these triangular voids that lack an inversion center. And so it's possible to take all these 1,200 structures and determine their symmetries and how they differ from the bulk crystals from which they come. And this is what you find. So the piezoelectric point groups are over here, left of this dashed line. And the monolayer ones here are the blue bars, and the bulk crystals are the red bars. And so you can see that really there's more kind of red bars over here on the centrosymmetric side and more blue over here on the non-centrosymmetric side. And so what this is telling us is that for a lot of these crystals, the bulk may be centrosymmetric and therefore not have this piezo effect. But as soon as you peel away one layer, this is something that can emerge in a single layer. And furthermore, for the particular form of the piezo tensor that you are looking for, you're likely to find a 2D material that has that form determined by the point group here. So for example, there's a lot of materials that have point group 1, which is essentially no symmetry. But there's a bunch of others here too. So if you're interested in a particular type of electromechanical coupling, say like applying a vertical electric field and getting an end plane strain, something like that, you're likely to find at least several 2D materials that have that particular type of coupling. So okay, so that's the database. That's all I'm going to say about the data. And so the next question is, how do we use this to predict what's likely to exist? So we have a whole lot of examples now of things that are actually 2D, and we want to use this to try to fill in the gaps. So given all these examples, how can we somehow infer what other chemical formulas are likely to have layered forms? And so in this particular example, this is how we've approached this problem. So let's say you have a chemical formula like MOS2, And we want to determine, we want to have some kind of model that tells us just something simple, just a binary output, which tells us whether it's likely to have a layered phase or not have a layered phase. So that's all we're asking of this model. And first thing we need is the data. So I showed you the positive examples. Those are the chemical formulas that we know have a layered phase, but we also need negative examples. And that's the crux of this problem. That is the tricky part. So the negative examples are cases of chemical formulas that we know do not have a layered phase. And this is subtle, so I'm going to talk a little bit more about this in a minute, but let's suppose that we have also a list of negative examples that we know definitely don't have a layered phase. So then you take this chemical formula and you parse it out into features. So for example, one of these features which has some kind of physical motivation could be, say, the average electronegativity of the elements that make up the chemical formula, weighted by the stoichiometry, or maybe the average atomic weight of the elements, or maybe the standard deviation of the atomic weight, or the electronegativity, or something like that. So these are things that have some kind of bearing on the chemical makeup of the material, but it's a little bit fuzzy, right? So it's not clear how to put these pieces together to construct some kind of physics-based relationship that tells us whether something is going to be metastable and synthesizable. And so that's where the data comes in. And so we take all these features. In our particular case, we have about 100 of these features that are things that are plausibly related to the chemical stability of the material. And we train this model, which in our case is just a binary classifier. We're using a support vector machine, which has these two outputs. It tells us whether the material is going to be layered or not. So that's the three pieces. So the data, positive and negative examples, features, which are physically motivated. We don't quite know if all these features are relevant, and we don't quite know how to put them together to construct a physics-based theory. And we're hoping that the data can help fill that in. And then the model itself is just a support vector machine, which is a binary classifier. So now about these negative examples. So this is really the crux of this problem. I mentioned toward the beginning of the talk that really this is all about data, or kind of 80% of success here is really about your data and how good it is, how complete it is. And the challenge is that in these databases like the ICSD, it may well be that there is a layered phase of a particular compound, but maybe it's missing. Maybe it's known, it's out there, it's in the literature, it's been synthesized, but it just hasn't been scraped up and put into the database. Or maybe nobody's tried to make it. Maybe it does exist, but it just hasn't been made. And so if we use the database to tell us which chemical compounds lack layered phases, there's definitely potential for being led astray. There can be bias in that information. And so we have to be very, very careful about doing that. So the naive thing to do is really just to take this database like ICSD and use it to tell us which materials do not have layered phases, with the caveat that there's potential to be led astray there. And so initially, that's what we're going to do. And then I'm going to show you a way that I think does this a little bit better. And so this is the support vector machine idea here. So let's say that you have these blue dots and the red dots, and this is just some two-dimensional projection of our high-dimensional feature space. And the red dots are the ones that we know are layered, and the blue dots are the ones that we think are not. And the support vector machine really just tries to draw, in this case, a line that will separate these two colors of dots, and to the to some best extent possible is defined by the support vector machine. And so the prediction for this particular case would be that everything in the kind of red or the sort of pink shaded region is going to be layered, and everything in the blue shaded region is going to be have no layered phase. And so when you do this, again, just making this very naive assumption about negative examples, you find that you can construct a model that has a precision of something like 0.4, 40%. Now, what that's telling us is that the predictions of this model are 40% of them are correct. And you might say, well, that's not too great. 40% could be a lot better. I would like a model that would, maybe do a better job making correct predictions. But really, the thing to compare with is how well does this model do if you were randomly guessing? So it turns out that something like 4% of known materials are layered. And so if you're just going through this list of known materials and trying to guess which ones are layered, and you're doing it randomly, you would get it right about 4% of the time. And so what we really should be doing is comparing our precision here of 40% to our random guessing baseline of 4%. And what that means is we're doing about 10 times better than random guessing with this model. And generally, to get some kind of, have a little bit of confidence in the model, you want to have, factors of 3 or something, at least a factor of 3 better than a random guessing baseline. So this is, probably statistically significant. There's really some signal here in the data and the features that we have that are leading to some predictive power. So that's for the case where we're making this assumption about negative examples. Now, one question is, can we do better than that? So we've also considered this what's called semi-supervised learning approach for determining the negative examples. So this is where we have a data set where one label is known. For example, we definitely know which materials have layered phases, but the other label is not known. So we don't know precisely which ones do not have layered phases. So this is how this works. So this starts out just like I was showing you. The first step is just training a normal support vector machine. You get a decision boundary here that separates the blue dots from the red dots. And now there's an additional step. So you use this boundary to determine for the unlabeled data, for the ones that we think are probably not layered, you determine a likelihood that these unlabeled points are unlayered as determined by the distance these points are from the decision boundary. So these points, these blue points that are really far away from the decision boundary, deep into the blue region, we would say are less likely to be layered than those that are found on the other side of the boundary that are deep into this red region. And these guys, they're blue dots, but we could say that, well, they're kind of mixed in with the red dots. And so maybe they're actually, these are unlabeled points, but, actually maybe there are layered phases that we just don't know about for these unlabeled points. And so this is the idea. You establish some kind of probability, and then you retrain another support vector machine that will give you a new boundary here, this solid line that will separate these points. And so now this new boundary, the semi-supervised boundary, is telling us that actually these blue dots that are mixed in with the red dots are actually probably should be red dots. And so it assigns that label to them. And so this is another way to utilize the information that you have to establish negative examples. And when we do this, we actually get a model that's pretty similar in performance of the one I just showed you. It's actually a little bit better. I think it's 14 times better than random guessing, but I would call that pretty similar. And so we think the predictions we're making here are relatively robust to several different assumptions one could make about negative examples. And that there's I could give a whole talk on this negative example stuff. There's a lot more to this, but at the end of the day, you want a model that's robust relative to different assumptions that one could make about that. And so we think we have that in this case. So another way to benchmark this or understand how well or not this works is to compare it to humans, because of course, humans, synthesis chemists are not just random guessing, right? They've developed really deep intuitions over decades for what's likely to exist, and they can look at a chemical formula and just tell you whether it's funny or not, whether it's something wrong with it. And so, there's a lot of kind of human wisdom that's been built up, and we would like to know how this model compares to that as well. And so we've done a comparison. So this is the precision of the model here, and our random guessing baseline is down here around 4%. And this is the time it takes to make a prediction, because we care about that as well. We would like, ideally, to be able to screen, millions of candidate materials, millions of chemical formulas, and that means we need an algorithm that's fast. And so the compute time also matters. So this is where the machine learning algorithm winds up. It's about, as I said, 45%, something like that, in precision. And let's see what happened here. Okay, so we put together a quiz, which looks like this, and we gave this to different sets of people, humans, and so we asked them to look at this list of chemical formulas and determine which ones are 2D. And if you're like me, you're totally lost. I think I took this multiple times, and I think I got 0 on every time I took this. And I think the one that's actually layered here is 16. This one is layered. But anyway, this is a hard, from my perspective, this is a hard quiz. I'm not a synthesis person. But anyways, that's the kind of quiz we gave to people. And so we gave this to about 36 what we call expert practitioners, who are people who are actively working with 2D materials. These are double E's and mechanical engineers and physicists and people who are making devices and so forth. And so this is how they did. So they did a little bit better than random guessing, which is good. So they have some intuition there, but it also took them a long time, because they were Googling things and they were kind of thinking about this for quite a while. And so they're quite a bit slower than the algorithm itself. And but really, the key test is the synthesis chemist, the people who really think about this on a daily basis. And so we gave this to several very bold, good sport, mid-career, inorganic synthesis chemists. And one of those individuals actually essentially he beat the algorithm. He tied it. And this is Josh Goldberger, who's at Ohio State. And so his precision was comparable to the algorithm. Of course, it took him longer because he's human and he's kind of thinking about this for a while. But the other synthesis chemists didn't do as well. They were quite a bit lower in precision. So Josh seemed to have some kind of magic touch in figuring this out. And so we asked him how he did this, and he gave us a list of kind of his algorithm that he used to do this. And he said he threw out things that have weird stoichiometries and weird as defined in his own terms. And he had some other rules. And essentially, if you take the rules that he used, you can find analogs of those in our feature space. So we think this is part of the reason why he's kind of comparable to the algorithm, is that the rules that he used are really also included in to some extent in the features that we've encoded here. So essentially, the algorithm is comparable to We think, some of the best mid-career organic synthesis chemists. And so now if we run this, we can screen, millions of materials. And what we find is that there are probably something like 1,000 2D materials that are synthesizable but have yet to be synthesized. And so that essentially means that we're about halfway there to finding or synthesizing all possible 2D materials, because I mentioned, we know there's about 1,000 or 2,000 that have been made. And if there's another 1,000 left to go, it means we're roughly halfway there. So I think that's kind of interesting to be able to say, how much left there is to do, in a certain space, because there are 90 something elements, and that's finite. And so, there should be some limitations on the number of materials that are available that those 90 something elements can provide. We've also, to some extent, tried to elucidate the properties of these materials, in addition to just predicting whether they're stable or not. And you can do that to some extent. So we've done band gaps here. We're trying to predict which of these candidates are likely to be metals versus large band gap materials and so forth. And so this gets a little bit tricky because you're taking your data and you're parsing it into smaller pieces. And so the precision here, the performance of these models tends not to be as good as the one that predicts whether the materials are stable or not. But to some extent, we can make these guesses about some of the optical properties, for example. And we've also done some validation with DFT. So we took some of these predictions and we actually did some DFT calculations on them, made some assumptions about what structures they could be in, and did some stability calculations, tested the phonons for stability. And we find that there's something like 13 out of 16 success rate for the model. And that's a little bit high. I think there's some bias here. As I mentioned, the model we think is actually probably closer to 50% success rate. So this is probably a little bit inflated, but the point is that this is really predicting things that we think are synthesizable. And then lastly here, going back to this question of, is the model predicting anything that you wouldn't guess from simple elemental substitutions on known compounds in the database? And so what this is showing here is this is number of materials on the vertical axis, and on the horizontal axis these are all chemical families. And I've removed the labels here because there are too many to label. But each of these bars corresponds to a chemical family, and the known materials are in red. So these are the red chemical families that I showed you earlier. And the ones that are predicted by this model are in blue. And so what you see is that for some of these cases, the model is just predicting elemental substitutions on known chemical families, like this particular case here. But in other cases, there's only blue. And that means that the model is really predicting new chemical families that you wouldn't find from simple elemental substitutions on known compounds. And so the model, we think, is really doing this thing that I mentioned earlier, which we really want, which is going beyond this kind of simple elemental substitutions and really trying to predict new compounds. And so we're working with others on trying to synthesize some of these and trying to get statistics. This is a challenge, as soon as we translate into the experimental domain, that things take longer. And, ideally we'd like to do some kind of high throughput experimentation with this, but, we have to sort of collect data points slowly typically, but we are starting to get some statistics on, how well this really translates into the lab. Okay, so I actually don't have a clock here, but let me take a quick look at the time and make sure I'm not blowing way over my, okay. So maybe just in the last couple minutes or so, I want to give you a sense for what I think is exciting about this kind of combination of data and kind of fuzzy physics and chemistry to make predictions, and what it really is enabling that's new, going beyond just kind of speeding things up that we can already do. What's really new here, and what are the aspects of this that we're going to be using, 10, 20, 30 years down the road. And this is kind of what at least one of the areas I see this really having a lot of impact. So in a lot of material selection problems, the real bottlenecks are, well, let me back up a little bit. So let's consider the case of batteries. So of course, there's a lot of interest in finding new chemistries, battery chemistries. This is a canonical material selection problem. And if you look at what the real barriers are to finding new materials, and you kind of look at the sort of academic literature, and then you talk to the people in industry who are really trying to actually make real devices, there's really a disconnect. And the disconnect is in a lot of the research, there's narrow focus on maybe one or two of the properties that are really required to make a viable battery. For example, let's say you want to find a new electrolyte, new solid electrolyte for a battery. You want good ionic conductivity, of course, for high power, and you want to have some kind of chemical stability, electrochemical stability over a certain voltage range. And these two things tend to get a lot of attention in the research domain. But then you go talk to industry people, and if you come up with a material that's great in these two properties, they're going to say, well, it's missing, we have, it's too expensive, or we have device integration issues, it reacts with our cathode or something like that. Or there's some, processing issue. They have to, center it at some high temperature that's going to, wreck everything else that's in the system. And so these are really the things that wind up being barriers. So it's not, what we're finding is that it's not one, magic property that is the bottleneck. It's really the combination of all the things that you care about to make a device. For example, in the case of batteries, we've done some work showing that really something like 10% of all known lithium conducting materials have ionic conductivity that are good enough for batteries. So that's not common, but it's certainly not rare either. And if each of these properties on this wagon wheel is something like 10% of materials have that property, and they're all uncorrelated, now we're talking about 10% times 10% times 10% times 10%. And that very quickly whittles down the space of materials that are going to work for your particular application. And that really seems to be the key bottleneck. And so what I think the opportunity here with these models, statistical models, machine learning kind of models, is to develop models that really holistically consider all these metrics, or as many as possible. And that's, I think, really going to help take the predictions that we're making in the kind of research domain and help push them into the commercial and application domains. And so we've been doing this in several different spaces. Batteries is one. We're doing this in some electronic material spaces as well. And let me just tell you, in the case of batteries, we did some work, this is again, maybe 5 years ago, predicting a number of materials, solid lithium ion conductors for batteries that satisfy most of the properties on this wagon wheel here. And we're finding, so we're pushing some of these into the lab. We have experimental collaborators here at Stanford who are working on this. And I will say that we're getting some very exciting results. I'm actually not allowed to talk about it, but I will say that I'm extremely excited about one of these families of compounds, this lithium boron sulfur compound, which we think is essentially superior in terms of ionic conductivity to the known solid electrolytes. This is ionic conductivity here. And we also think it's superior to all the other sulfur-containing solid electrolytes. And it seems to have a high kinetic stabilization, which is making it sort of, pushing it out into this higher stability region with some of the oxide materials. And so we think this works. I mean, we're essentially finding materials that are coming out of this that really can check a lot of the boxes that make it useful for commercial applications. And so anyway, so this is really, I think, one of the big impact areas is the ability to now consider the full spectrum of requirements that you need to really push something into the beyond just the research domain and into the commercial domain. And that's something new. That's something we really couldn't do before, because evaluating each of the components on that wagon wheel is just too expensive with traditional approaches. So I think my time is up, and so I will end by acknowledging the people who did this work. It was primarily done by student Gu-Woon Chun, who's just graduated. She just started at Google, and also Dosh Chubak, who is also, he's a former postdoc. He's at Google as well, worked on this. And I also want to acknowledge Josh Goldberger and some of the other individuals who took the survey for being good sports and putting up with this, because we really learned a lot from that process. And so with that, I'll turn it back over to you there in the lecture hall, if there are questions.
Okay, thank you very much, Evan, for a very nice talk. We just have a few moments for questions or comments. Are there anybody who would like to make a comment or question? Ah, okay, if you will.
Thank you. I wanted to ask if there are any possibilities for hybrid approaches. So like using simulations that have, like compared to full simulations, don't require as much computational power, but feeding that in as a feature into the machine learning prediction algorithm.
Yes, certainly. So what we've done here is focus on features that are fast to evaluate. So none of these features require any serious computation. Certainly none of these require like a DFT calculation of something. And that was really by choice, because we want the model to be able to screen millions or even billions of materials, depending on how you parse things out. And getting to those scales requires getting away from the DFT calculations. But certainly, if we were looking at smaller spaces, we could consider DFT-based features. And it's something we haven't done just because, as I said, we really ideally want to be able to screen these very large spaces.
Okay. Any more questions or comments? I have a question. So you were trying to find 2D materials which were weakly bonded in one direction. So equivalent to, let's say, so you could exfoliate them, I guess. But there are many materials which are innately two-dimensional, but structurally not two-dimensional. For example, I'm thinking of the dolophosites, which are highly two-dimensional, fantastic conductivities in plane, but very poor conductivities out of plane. So why are they not interesting to you?
Let me clarify your question. So you're asking about materials that are isotropic, they're highly isotropic in their properties, but not necessarily exfoliable into thin films. Is that right?
Yes, that's right. Yeah.
Yeah. So I wouldn't say that they're not interesting. I'd say this particular case we focused on the layer materials because that's a subcategory where we think the chemistry is relatively homogeneous, and more recently we've expanded this out. We have a manuscript now, which is we're in the process of submitting, which is really expanding this to the broader classes of materials beyond just the 2Ds. And so, high anisotropy, highly isotropic property materials that are not necessarily layered or Van der Waals compounds are in that particular category. So, so there's no, to answer your question, try to answer it more succinctly. There's really no, deep reason why we're limiting this to 2D materials, except that this was our initial set of materials. We thought that the chemistry would be relatively homogeneous and might be easier to describe with an approach like this.
It just seems to me that it's even more interesting if you have materials whose dimensionality is related to the property. In other words, they have properties, some which are three-dimensional, some which are two-dimensional, some which are one-dimensional. In other words, they're multi-dimensional. That somehow seems to be even more exciting and interesting. I mean, I guess the interest in these exfoliable materials is maybe you can form heterojunctions with them, but then of course they have very weak interactions that maybe precludes that. So it just, it's not clear to me that these are the most interesting sets of materials.
Yeah, I completely agree with you.
Okay, I just wondered. Okay, fantastic. Are there any more questions? I'm sorry, I don't see any in the chat, so I want to thank all of our 4 speakers today who gave very nice talks on different subjects, and we thank you very much. And we just want to, of course, point out that tomorrow we have 3 more talks in the afternoon, and hopefully many of you will return to listen to those 3 very interesting speakers. But again, I really would like to thank, on the behalf of Joyce and myself in particular,